Good morning, everyone. Yeah, I'm new here, but after these 3 days, I think I have had the opportunity to meet most of you, so pleased to meet you. And I come from a different world than most of you. I come from mechanical engineering and material science. I've been working in metallurgy. I'm mostly working in what we call computational material science. I've been working in different models at the university, but also working very tightly with the steel industry. And we work in models that they use to design new steel grades, to see how they can improve their production processes, and so on. These are sometimes quite complex models that require quite some knowledge. And they are usually written by PhD students who don't have any idea about programming beforehand. There is a lot here. It doesn't feel very well, and the idea is try to fix that. I think that APL could be the right tool to fix that. So I'm going to talk about this project, Dyalog and Academia. I thought a lot if I should use the glyph or not, but then I thought, well, it's the logical end, and what I want to show is that this is a logical thing to do, so I went with it. It will be a very simple presentation, no hard technical stuff, so sorry about that, I know you love it. And I will start talking about academia. Most of you, I guess, have had some contact of academia. Is the university at the end. Is where you go to learn, where you go to acquire knowledge, but also, at least in theory, where knowledge is created. So we have education, teach what we already know, but also research, learn new things that we can teach later. In particular, in technical universities, is also the bridge between science and engineering. We tend to mix these two terms, but I like to make the distinction. I really like this quote from a classic textbook on machine design. It says that engineers use science to solve their problems. But even if the science is not available and you solve the problem, you are doing engineering. Another way to say this with other words is that science is understanding how the world works, and engineering is making things work as we want. And of course, all of this is interrelated, and the goal is to put Dyalog APL at the middle of this. We want to use it for education, for research, for science, for engineering, and that's what we will try to do. So, what's the goal, more specifically? Promote the use of Dyalog APL in academia. We want to get visibility in academic circles. Most people studying, for example, mechanical engineering, they have no idea at all what APL is. They don't know they have this tool available for them. There are also some things that probably Dyalog can learn from academia about the way they work, the problems they have, and how they try to solve them. And we want to see if APL is the right tool for that, and if it's not, try to fix it. In general, introduce a new generation to APL. There are some people here that are, let's say, the less young people, that they learned APL when they were studying. And there are also some very young people here who learn APL in, I don't know, in some YouTube video or because they read something in Reddit or Hacker News, but they are not learning it at the university. I think they should. And in general, we want that there is a good relationship, some back and forth between academia, APLers, Dyalog, so on. So how to do this is not an easy task, of course. So we will have to work together with academia. By the way, I will say we a lot And it will be an ambivalent we. It can be we Dyalog, we academia, we me and you. Yes, you will figure it out. And first, the first step, because academia is very broad. So we will focus in a specific university and even more in a specific department inside the university, the Material Science and Technology department. The idea is to take part in academic life, be part of it, and apply APL to the solution of the problems that we have. And participate in the research projects and also participate in the education of the students. And teach them APL and show them what they can do with it and establish these contacts. Okay, I guess most of you, or at least many of you, don't know Ghent University. I will talk a bit about it. It's in the city of Ghent, in the Flemish region of Belgium. It's a quite research-oriented university. In fact, their motto is "Dare to Think," which could also apply to APL, probably. And it's not the largest university, but it has about 50,000 students, 50,000 staff members. Or how I like to look at it, they have 65,000 potential APL users. And then I will focus a bit more on the Material Science and Technology department. Here is where I did my PhD some years ago. It's part of the Faculty of Engineering and Architecture. And we work a lot on research, very close with the steel industry. We have this material research cluster, and there are some important companies there. ArcelorMittal, which is the largest steel producer, is not far, for example. And the main focus of the department is metallurgy, metals. We do some work with aluminum alloys, titanium alloys, but mostly steel. Steel is the big thing in metallurgy, of course. And you may think at this point what all this physical metallurgy so on has to do with APL. So I would like to show you some of the problems we need to solve here in what we call, as I showed you before, computational material science. I will talk about a few of the problems, a few of them. I will start with microstructural analysis. Here, what we do is we have scanning electron microscopes, and we use that to look at samples of our materials. And with this, we get lots of data. We get millions and millions of data points. And for all of those points, we get a lot of information. Sometimes chemical composition, sometimes the orientations of the materials, things like that. Then we need to process all this data. Something we do is to divide the material in grains. I don't know if you know it, but metals are crystals. They have a regular structure. Inside the material, there are regions with different orientations in which these grids are oriented differently. And they're really important for the properties of the material. And we need to calculate distributions for all of these. There are a lot of statistics, but this is not always easy. Orientations of 3D bodies are 4-dimensional objects. Then we need to calculate distributions for this. We use something called generalized spherical harmonics. It gets quite complex very fast. But it's a very important aspect of our work. What we do with microstructural analysis is the output of our experiments, but it is also the input of our simulations. So it's very important. So what simulations? For example, crystal plasticity. In crystal plasticity, what we study is the deformation of the materials. So we work at what we call the mesoscopic scale. The macroscopic scale would be what you can see with your bare eyes. Then we have the microscopic scale, which is when you look really, really closely with a microscope close to the size of the atoms even. And here we work at the mesoscopic scale. So for example, those cubes with a few grains, they would have around 50 micrometers, something like that. And this is a very interesting problem because it mixes a lot of things. You need to know material science and crystallography to deal with the orientations of all this. You also need to deal with mechanical engineering, with tensor algebra at the end. And they are very complex simulations. You write your model, you have normally some commercial solver, and you send your job to some cluster. Normally, more universities have some cluster or whatever. And the simulations are running for days, even for weeks. And it's horrible. Sometimes they fail, and after 2 weeks, you get a message that tells you there was an error. And then, you cannot add a few printfs or something like that and run it again and hope for the best. It's horrible to work with it, really. So we have different mathematical methods to solve it and so on. It's an ongoing problem. There are many models, all have their advantage, their disadvantage, but there is no perfect one, no silver bullet. We also work with transformation models. This is kind of similar. Even crystal plasticity, what we do is to deform the material. Here, what we do is to apply thermal treatments to them. Sometimes we heat them up, sometimes we cool them down, and with this we have phase transitions inside the material. Here you can see, for example, an example. Here at the top left, you will have a very deformed material, and you heat it up a little bit, and then new grains start appearing, and so on. And we solve this with different methods. For example, a very typical one is using cellular automata, but I'm quite sure you cannot write this one in a single line. It can be quite complex. You need some nucleation laws, then some growth laws, and indeed, quite complex. So these are difficult problems that normally a PhD student takes a very small subset of these, like, for example, the nucleation of a certain steel phase under certain conditions. And he's working on this for 4 or 5 years, and he makes a very small advance. So these are hard problems. I hope we can tackle them at some point, or even better, that we can convince the students to tackle them with APL. But for the time being, I'm trying something simpler, that is analysis of tensile experiments. This is a bit the bread and butter of mechanical engineers. What we do in a tensile experiment, we have a specimen of our material. We pull from it until it breaks. And then you get a graph like this. You have in your x-axis the strain, the deformation, and on the y-axis the stress, which is related to the force that we apply. And from this curve, we need to extract some series of properties. And I don't know if you can notice it. Here you have some experimental scatters. You have some points that shouldn't be there because our data acquisition cards don't always work and so on. And then we have to do some simple processing. This is a problem that I have solved along the last 15 years. I think at least with 5, 6 different languages. I did it with, with Visual Basic macros, with Oak, with Fortran, with MATLAB, with Python. And now I did it with APL. And I'm very happy with the result. You can see at the right the line count that I have, and you can see that I have a few functions, but most of them are 1 line or 2, 3, with the exception of plot, which is just generating the plot. So there you need a lot of lines to set up the captions, the colors, so on. And I also have that demo, which is what I'm using as a pull replacement for test and for documentation. I will work in that at some point. And what I really like about the APL solution is that at some point I need to explain to the students what we are doing, what they need to do. And I cannot show them the 500 lines of Python that I have and explain it to them. They don't know Python either. But I think I can show them the APL expression and explain that to them. And I think that APL can be the language to talk about it, but also the implementation language is a huge advantage. So the idea is to start a bit with this kind of simple projects, show it to them, and hopefully they will pick it up, and they will start using APL in their own projects too. So what do we want to do with APL and research? As I was saying, we want to use APL to solve these problems. And then what we will do is to compare it with the solutions we have in other programming languages, which we already have. And the idea is to be honest here. Sometimes APL will be better, but sometimes we will find some points in which we can improve APL, maybe the documentation, maybe the way in which it is presented, so that the students can use it as a useful tool for their research work. And eventually, hopefully, there will be some presence of APL in research publications, in conference. People, mechanical engineering and material science will know that there is a tool called APL that they can use. And we will also use it for education. So we will use APL to talk about difficult topics, to see how they can solve them. And we will define our models, our mathematical methods using APL. Many times, we don't have any standard notation at all. In fact, the way I arrived a bit to APL was because I was searching for a notation I could use. Everyone used their own, and it's a total mess. Total mess, really. And I think that APL would be a better tool, but well, we have to check if it can be used. I have listened many times that APL is the right tool for education. That's what it was created for at the end. But we want to prove it. I'm a scientist. We are going to do the experiment. We are going to show our results, and we are going to discuss them and work from there. And eventually what we want is to have more presence there so that the students know APL. And hopefully in 30, 40 years, there will be people coming to the Dyalog conference and they will say, I learned APL at my university in my material science students. That would be nice. There are probably also some things that Dyalog can learn from academy. You will find new problems, new interesting problems. Yesterday, for example, we showed the student competition and these small problems that they have to solve. We have lots of them, lots of every level that you want, we have lots of them, and they need to be solved. Many times we don't have a good solution. I'm sure any student could come up with a good solution using APL. You can also learn about different workflows. Here, on the one hand, we have a constant flow of new students, and there's also something that you see in the student competition. They bring new ideas, they have different ways to do things, and there is a lot to learn. On the other hand, we have some very bad habits sometimes. We in material science, we are not good programmers. We do many things wrong. And having the right tool can help you to go in the right track. And this is probably something that Dyalog can also learn from us, how to take us in the right direction. And And well, yeah, also Dialog hopefully will be part of the publications of the conference or so on. Eventually will take part in research and innovation. And well, I think that at this point I'm starting to repeat myself a little bit, so I will leave it here in case you have some questions. And yeah, that's all. Thank you for your attention.